But then, well, one question could be how can we actually control this complexity, right? And one curiosity I had when I was looking at the videos was that, I mean, there is a lot of research on muscle synergies. So in general, the concept of synergies as a way to simplify the complexity of the motor control. And I was wondering whether I mean, if we assume that our brain is exploiting this dimensionality reduction to simplify the biomechanics, can this also mirror it on the impedance domain and somehow simplify the problem also on the dynamical point of view? No one has an opinion on that?
Maybe you can volunteer somebody.
Yeah, I would love to hear the Eric has on that, because yeah, I remember that discussion on similar topics a long time ago.
So I think, you know, the concept of muscle synergies is important. And because of the many redundancies we have in our neuromotor system, right, we've found solutions that work across a broad range of tasks. Whether those are, you know, where they're encoded, I think is somewhat irrelevant. Behaviorally, they clearly exist. And there, with those, there's going to be a mechanical consequence. So if I activate a set of synergies to simplify a control problem, there's going to be a corresponding impedance for that. Now, whether or not the synergies are explicitly used to control impedance, I think is a different question that I'm not sure if anyone's, I'm not aware of anyone who's addressed that well, but it's a good one to look at.
Thanks. Okay, if there are no other comments on that, another point we want to discuss in this session was, I mean, we saw a lot of solutions in robotics that try to optimize to find the side profile for the impedance, and others that essentially exploit the learning, right? Different kind of learnings. So our question was, what are the limits of optimization-based techniques? And when do we need to go for learning techniques? What is the threshold? I know Professor D'Angeli do a lot of research on that topic. So if you want to start with. We can't hear you.
Yeah, I think now I am muted. Okay, of course, I think optimization approaches basically you assume that you know what is the cost function, right? If you don't know it, then of course learning-based approach would be maybe it tries to guess it from the data, right? So you tries to gather the human data, and then from the human demonstration, tries to find it out what would be the x0 and also what would be the appropriate your impedance parameters. And a lot of works are there tries to somehow relate between the variances of the data to the impedance parameters. I think these are one of the strategy also people doing it, and then I guess probably that is where people think maybe it might be better compared to the optimization based approach. But also there are works which tries to combine learning-based approach together with, again, the optimal stochastic optimal control approaches. So you try to get this, the nominal trajectory, and also you try to get what is the variances, and then using those information again into your optimal control, like LQR formulation, and tries to minimize your cost function, reducing your control inputs as good as following your trajectories, right? The x0, which is you found from the demonstration, but also you try to put it the Mahalanobis distance like things inside of the LQR. And then this Mahalanobis distance is also coming from the human demonstrations, right? So you try to put your variability inside of your LQR formulation, and then tries to calculate what would be the optimal stiffness from this LQR. So this is kind of another way people tries to combine the learning-based approach together with optimization approaches.
Okay. No one has comments on this?
I have a follow-up question. We talk about like the role, the learning of impedance, but also what is the role of impedance during learning? Right. So I think about like if I were to learn trying to learn how to do a tennis serve, for example, and all I have is visual information, I might be doing something like, high stiffness motion control. Then I start to, actually interact with the racket and the ball and whatnot, and then how that changes. But I feel like it's not often considered, or is it even worth considering how modulation of impedance might be useful in the learning process?
I guess the people are also doing a combination with the reinforcement learning, actually tries to kind of modulating your stiffness while trying an error, and then modulating that in order to aim at your task performance. And then of course it's again, you need to define your reward function on there. Yeah. So this is there are some works on doing that, also combination with the variable impedance control, actually. I think maybe Ludovic, maybe also you worked on this?
Yeah, so I guess there's something that is difficult if you do reinforcement learning is that you need to generate good data that you can use. And having a system, so if you have let's say you have a double inverted pendulum and you just let it swing freely, your data is, the trajectories are so unpredictable that you cannot learn anything. It's very hard to learn anything out of that, right? If you had a lot of damping in your system, then it becomes trivial, and then it's really easy to learn what the system is doing. So I guess maybe, and I don't know if it's true, right? But maybe, higher stiffness, higher damping allows you to generate data that is more predictable. And maybe it allows you to learn something, right? If you would not have any of that, and you just let your mechanical system freely do whatever, you would not be able to learn quickly enough, maybe. It's an hypothesis. I don't know if it's true.
Yeah.
Yeah.
I mean, and even like, thinking about like some of Dagmar's work and like this like discrete throwing task, right? Or just even watching people perform this task, you look from these, very discrete movements, but over time, they start to blend and look like these rhythmic movements. And is that does that have something to do with, you're now now you can perhaps be more compliant and allow joint oscillations to occur once you feel comfortable, right? And so it's interesting to see in humans, you do see this, like there tends to be this relationship between like expertise, and then we say, we say it that motions make something look effortless, right? One could argue maybe that's you learn how to do it in an energetically optimal way, right? Or it's something to do with actual learning of the task. But I think it's something that we do see throughout the course of learning, at least in human behavior.
Okay, so I would like to change a bit the focus, and I would like to come back on the point of discussing the interaction between humans and robots. And one question I had when I was looking at the presentation of Professor Bourdet, but also David's presentation, most of the presentation of this workshop was that we assume that when we interact with a robot that is compliant, we feel this as a natural behavior. But are there studies that try to understand how we react to an interaction with a device that is changing its dynamical behavior? I'm thinking especially on David's work on
Yeah, like, so the probably kind of like, let me give a little bit of context. So let's assume a spring in parallel with the leg.
Mhm.
So the question could be, how would a spring force imparted in a human body change the behavior of the human? And well, this is a difficult question to answer. Probably experimental investigation is required to answer this question. But maybe we could go back and see some of the examples that are out there, some of the devices that are out there, and then see how humans use them and how we can learn from what is out there already. So if you consider an ice skate is not a spring, of course, but it's a device. It completely changes a gait. So there is no, ice skating is not like running. But still, while it completely changes a gait, it allows the human to move almost 50% faster than without an ice skate. Now, we could argue that this is because, well, the ground is not like an ice takes away collisional energy loss and so on and so forth. But, well, if the foot doesn't slide on the ground, then there is no collisional energy loss in running also. We can take another example, which would be a bicycle. So the bicycle is a very interesting example because we often consider a bicycle as a nice device, a perfect device to provide energy. You have a pedal, you can pedal in the air. So during running, we cannot do anything in the air. In the air, we just swing our legs. So in the bicycle, you can pedal in the air, you can supply more energy, you can go faster. But there is another interesting thing. So bicycle has a seat. And like the force it imparts to the body is minimal compared to a spring. Of course, so this question is very important. How much force is like the human body experiences might affect of how well an energy can be generated, how well the muscles can be used to provide more work, more energy to run faster, to move faster. I would stop here.
But then my doubt was if I mean, we know that interacting with a robot that moves as a human would do is better because we can predict how it will behave. And I'm still not I'm still trying to understand whether this I mean, behaving at the dynamic level as a human would do may be relevant to improve this perception of human likeness in the robot, right? And this is still a point that, to me, it's interesting.
Are you saying that the robot needs to be compliant when it interacts with a human all the time, or is it something that would depend on the task?
I think it will depend on the task. Yeah, definitely.
It will definitely depend on the task. Actually, of course, so we have spoken a lot about shaping the impedance or changing the impedance to shape the interaction with the environment, the mechanical interaction with the environment. But actually, impedance can also be modulated to change the sensing of the environment. Because so you have a dual role, right? That's something that is specific to haptics, right? That you have both the mechanical interaction, so the energy exchange, and you have also, of course, the sensor, the information about the sensing. And so we have done some studies. So for example, when you put two humans who are connected mechanically, we found recently that they change the impedance in order to better sense a partner. And so it's not only the energy, it also is the information, and that's something that is interesting. And of course, so you were asking, so what about human like? I mean, to me, I mean, in a way, there's nothing that is human-like. I mean, in a way, we don't care whether it's human or robots. But what is sure is that by looking at the human, we can, at least in my case, I can think about things that I wouldn't think otherwise. And then I can go back to the robots and maybe develop technique for the robot and also use the robot to verify, to test the human and to verify what I find. So that's the way I see.
Crazy that, I mean, you talk about human-like. I mean, it's interesting if you think about the future when we have robots in the real world, and I don't know, they're moving around. You know, when I look at another human, right, like I'm implicitly making some assumptions about how it's going to move. With a robot, you have no idea, and it can look identical. It can be the same, whatever. Pick your favorite brand robot, and depending on, you know, this controller can change. And so it's actually a really interesting question when you think of from a human learning standpoint, is how are we going to develop these internal models once we actually start to experience it and interact with robots, and what's going to be the implication if they're all controlled differently?
I guess we will learn how to predict how robots behave, right?
Exactly. Yeah. I guess that's a future us problem, right? But I mean, I guess like I'm at the stage where like I'm still looking at my robot and I'm just like, in what way are you going to disappoint me today when I turn you on, right? But you can extrapolate that into real world applications, and just that, like, you know, it's still daunting, even us like who've been experienced and, you know how a robot's going to behave. You go to another lab, you don't know how that, you don't have a good sense of how that robot will behave. And then, you start to think about like that problem can then magnify once you get into the real world.
So I think the seriousness of that problem becomes more evident when you have more intimate physical connection between the human and the robot. If you have a full body exoskeleton, boy, I want to make sure it doesn't. I want confidence that it'll continue to get out of the way when it should, or not get out of the way when it shouldn't. I think the complexity of the system makes a big difference.
Yeah, and I think there especially you're going to run into the same problem that you run in with like self-driving cars, is that, I mean, I know from experience, sometimes my car will just stop moving, right? It's detected an obstacle, and it's a jarring feeling, like those, especially in those emergency cases. And as humans, like we don't really have a good understanding of how I think our smart cars are probably one of the most smartest physical systems that we have out there to date. And it's weird and uncomfortable when it does something intelligent. And we have little experience with it. And so I think you're going to have the same problem too once you start getting into wearing an exoskeleton and it's trying to help you, but you don't know how it's trying to help you. And so you try to fight it, and then disaster, right?
Well, one thing for that is that the robot definitely should understand the human.
Mm-hmm.
And then shape so adapt the behaviors that correspond to that human. Yeah. I mean, if you don't have that, of course it will not work, right? And it's also is why we can understand each other. I mean, why we can work together, because we understand each other. So we identify the partner force, impedance, motion intention, and yeah, because we understand, we can adapt. And if you give these to robots, then maybe may not notice that you interact with a robot, right? Because it would correspond somehow to your intention.
No comments on that point? Megan,
No, I mean, I think
you're
it's,
convinced.
it's funny because yes and no. It's interesting because again, this maybe gets just, you start to get very philosophical, right? But I think like, you know, there's some people I would prefer to put IKEA furniture together with than others. Like over, you know, so on one hand, like how, you know, how much are we going, you know, and I just obviously don't know the answer, but when it comes to adapting to human preferences, how much is it that the human will have to adapt to the robot, and then the robot vice versa? And I think, yeah, we just don't, that's what we're trying to figure out, right?
I think you are right. There is really mutual understanding is there, and then there are really a lot of interactions between, right? Robot tries to understand the human, and the human tries to understand the current robot's control schemes, and then again, vice versa. There are a lot of iteration, and then a lot of adaptation will go on. And then I think robot should try to find it out from this interaction, what would be the preferred, right? The physical interaction, the scheme should be for this particular person. Yeah.
Yeah. I mean, also, and you know, I mean, as humans, we also have this verbal communication, right? Which, I mean, we don't we don't necessarily, no pun intended, talk about, that we can, at least we can give cues, right? I mean, for those of you who have been talking with lately, like I have a puppy, and I think like, man, yeah, we could physically interact with each other and we can communicate from force, but it'd be so much easier if I could just be like, go, like, move here, follow me, and you know, those verbal commands were understood. So what's interesting is that, like, again, there is this mutual understanding or learning about one another through forces that we're applying, but then there may be a limitation to that, how effective just that communication can be.
Yeah, but you know, I mean, the communication between humans is also not perfect.
Yes.
I mean, so, you know, I mean, you will find the same limitation in bandwidth, in sense and resolution, and so on, right?
Yeah.
So we should not assume the human is perfect.
Yeah.
The human, yeah, you have the same hardware limit, and yeah.
Yeah. And so I think it's just an interesting question to think about, like, where, again, because we do talk a lot about, you know, predictability in human behavior, but then also when it comes to robot behavior, and just as we go along in this research, what does that actually mean? Or, you know, yeah.
Yeah, I think that's a good question, because stability is I mean, the human interaction is very, I mean, more than stable, robust, right?
Yeah.
And how we get that, it's still not very clear, I think. I mean, this robustness of the human behavior. Yeah.
Yeah.
Okay.
Well, as there is a long silence, I've been just pondering about predictability of human behavior, and thinking of the example of different cultural contexts, people that grow up in different cultures that have different behaviors. And I leave it as this thing. The question now is, it's certainly there's certain gestural components that one can pin down with kinematics and then assignment of meaning. But there is something beyond that. And certainly sort of stiffness, impedance may be one of the elements, but I'm trying to push beyond that just for pure brainstorming. What else is behind, let's say, that people coming from different cultures can be detected from bodily movements. So what is behind what we perceive as difference? I don't know, I'm just throwing it out.
Nice to see you, Dagmar. So I think it can somehow be detected, right? I mean, of course, you have to give a context, you have to give assumption, but it can somehow be detected.
I totally agree. I'm just sort of mulling over what else could there be, just trying to be not bound by the current discussion, but even going, is there anything else that we are not seeing right now? Fluidity.
So maybe what we have are different impedance accents. You know, you got an American style impedance or a French style impedance or an Italian style. Could be, right?
I'm pretty sure there is, but but I was just trying to think whether there is another concept which is outside this impedance workshop that might come into play. I honestly don't know.
I mean, I think that's an interesting question. I mean, even just getting back to like this idea of emotions, right? Or, you know, how we're feeling and we communicate that. Whether that's, I don't know if you intentionally communicate that or just that happens. But you can think about, I mean, if you take a very objective view of the human, right? You perhaps are modulating your impedance to communicate the state of yourself, right? And so I think that, I mean, that is interesting, right? Because anytime I lift my eyebrows or scowl, I mean, these are all, you know, these are all muscle, you know, muscle activation patterns, and while they might not necessarily have, you know, be directly responsible in terms of physical interaction, I might be communicating something about how how I would physically interact with somebody, right?
So there have been some really nice studies showing that you can determine someone's emotional status by looking at them walk, right? So you very much signal your emotions and your behavior and how you plan to interact with someone by how you move. So you don't even need a facial expressions to do this. Yeah. So that would be quite interesting to start thinking about how do you embed emotions within a robot and how you walk around in the environment and are about to interact with someone.
Right, and just to throw that in, it's well known that we also differentiate from the kinematic patterns, male, female, walking, right, as well as other behavior. So
what about handshakes? I mean, can you communicate via the firmness of your grip, which is essentially an effective hand impedance?